Assalamu alaikum everyone. Welcome back to Easy Taleem. Today is the final lecture of our Logarithms and Exponentials chapter. If you've been following this series from the beginning, you'll know that we didn't start by memorizing formulas. Instead, we asked a simple question. Why do logarithms even exist? Because algebra broke. The equation 2x equal to 10, 2 power x equal to 10 couldn't be solved using the algebra you already knew. So mathematicians invented a brand new function, the logarithms. In the second lecture, we built on that idea. We proved the three logarithm laws instead of simply memorizing them. We learned log of xy equals to log of x plus log of y. We also learned the quotient rule, which was log of x upon y is same as log of x minus log of y, and the power rule, which was log of x, the x being the argument of the logarithm raised to the power n, is same as n multiplied by log of x. We also solved logarithmic equations and discussed why checking the domain is absolutely essential. Today we finally use everything we have learned. Today you'll see why Cambridge introduced logarithms in the first place. By the end of this lecture, you'll be able to solve exponential equations that cannot be solved by ordinary algebra, solve exponential inequalities, understand why the inequality sign sometimes changes, and finally learn one of the most beautiful application of logarithms in pure math 3, which is linearization. This is where Cambridge takes a curved graph and turns it into a straight line. If you have ever looked at a linearization question and wondered why on earth are they plotting ln y against x, then today that confusion disappears. Okay, let's begin with the exact problem that created logarithms. Suppose I ask you to solve 5 to the power 2x plus 1 equal to 7. Can we make both sides have the same base? No, 7 isn't a power of 5. There is no algebraic trick left. This is exactly where logarithms become our tool. Now, here's something I want you to remember for the rest of your A levels. Logarithms do not remove power. They don't remove the exponents, they bring the exponents down. Okay, so that's the entire philosophy. So let's do it. Take logarithms of both sides. So I will put log on both the sides, and we can do it using the common logarithms or natural logarithms. I'll use logarithms with base 10. So if base is 10, then I need not write it here, and I will put in the argument 5 to the power 2x plus 1 equals to 7 as the argument of the other log. So basically I introduce log on both the sides, right? So this becomes, so now we apply the power rule, right? From our previous lecture, the exponent now comes in the front. So this becomes 2x plus 1 times log of 5 equals to log of 7. Now we can divide both the sides by log of 5. So this becomes log of 7 base 5 by change of base rule. Change of base rule, which says that log of a to the base b may be written as log of a to the base c upon log of b to the base c. So see how we had base 10 here, so c was 10, so we just removed that and instead rewrote it like log a to the base b. So this is same as 2x plus 1. Now subtract 1 from both the sides, so you get log 7 base 5 minus 1, and now we divide both the sides by 2, so we get x is equal to half times, you put the bracket, make sure that you don't forget it, minus 1, right? So now finally this is our answer. Notice something beautiful. We didn't invent any new mathematics today. Everything came from one idea, the power rule, right? That's why understanding the previous lecture was so important, and you can do that by going to our playlist on our YouTube channel, on this very channel, and watch this lecture on the 3 logarithm rules. If you only memorize formulas, every question feels different. If you understand the ideas, almost every question follows the same pattern, and Cambridge loves testing exactly that understanding. Now, solving equations is only half the story. Solving is only half the stories. Cambridge also asks exponential inequalities, and that's where many students lose easy marks. Let's look at that next. So far, we have solved exponential equations. Now, let's move to something that students often find more confusing, which is exponential inequalities. Okay. Fortunately, the mathematics is almost identical. There is only one extra idea that Cambridge expects you to understand. Let's begin with the easier case. Let's solve um, 2 to the power x is greater than 5. Exactly like before, we cannot rewrite 5 as a power of 2, so we take logarithms of both sides. So we take log on both the sides, so this becomes log of 2 to the power x is greater than log of 5. I'm deliberately keep using different color for the introduced function, which is log, so that you can make the distinction that we're introducing. Now apply the power rule, so this becomes log of 2 is greater than log of 5, and now we can divide both the sides by log of 2. Now this is the important question: can we divide both sides by log of 2? Yes, but before dividing, always ask yourself, is log 2 positive or negative? So by definition, whenever these arguments are less than are between 0 and 1, it's going to be negative. Whenever it is equal to 1, this is going to be 0, and whenever it is greater than 1, right, this is going to be greater than 0. Why? Because f of x, so if f of x is 10 to the power x, then this is how the function, the graph behaves, right? So at 10 to the power 0, it is 1, and beyond that, this is greater than 0, and before that, when x is less than that, it is just greater than it is greater than 0, but between 0 and 1. So it behaves in exactly the same manner, right? Now when you take the inverse of it, so between the domain of 0 and 1, the value is negative. At 1, the value is 0, and beyond 1, the value is greater than 1, right? So log of 2, because this is log of 2 and 2 is greater than 0, greater than 1, therefore this is going to be positive. So yes, we can divide both the sides by log of 2, and the sign is not going to change, right? So this is going to become x is greater than log of 5 over log of 2, which we can also rewrite as greater than log of 5 base 2. So you can either press this in your calculator, you have a button log, and then you also have another in your scientific calculator where you get, so this gives you this option, and there is another option where you get this by pressing shift sign or something, right? So this is going to give you a positive number, and this is going to be the range for this answer. So this question was pretty easy, right? Now, whenever you divide an inequality by a positive number, nothing changes. The sign does not change. We retain the sign, right? It is still greater than that. So, just like ordinary algebra. But now let's look at a question that Cambridge actually uses to catch students, right? So now if I ask you to solve, let me change color, wait. If I ask you to solve 0.6 power x is less than 0.7. Now again, take the logarithms on both the sides, so this becomes log of 0.6x is less than log of 0.7. Now apply the power rule, so this becomes x times log of 0.6 is less than log of 0.7. Now in order to isolate this x, I need to divide both the sides by log of 0.6, but I must ask myself first whether log of 0.6 is going to produce a positive or a negative number. Now that I know how this function behaves, since 0.6 lies in this domain, therefore log is going to be negative. Or if you look at the function, since 0.6 lies in this domain, the answer is going to be negative. Now, because when I press this in my calculator, this is going to be negative. Let's say this is negative 0.28. So this is nothing but negative 0.28x is less than, let's say, I'll keep it as it is. So now what I need to do is I need to bring this here, and this is going to become negative log of 0.7 is equal to, is less than 0.28, because this goes here now, 0.28 of x. Now this becomes positive and I divide it. So now this is going to become x is greater than negative, whatever this number is. Maybe this number is negative 0.35. I don't know. So I will write down negative 0.35. over 0.28. So this is going to be for 5 upon 4. Let's say I don't know what the answer is. So x is going to be greater than 5 upon 4. The answer is going to be positive because this is negative. This is negative. When you divide negative by negative, this is going to become positive. However, the sign is going to change. Make that distinction. Okay, now I'm going to clear this all up and we'll solve it again so that it is clear. If you want to see these steps again, run the video in 0.75x or something, slow it down and watch it again. Okay, now apply the power rule. This becomes x times log of 0.6 is less than log of 0.7, and because I know that this is negative, actually this doesn't matter whether this is positive or negative, but because I'm dividing both the sides by log of 0.6, which is negative, therefore this sign is now going to change, right? So now this becomes x is greater than log of 0.7, which is a negative number, over log of 0.6, which again is a negative number. Therefore this entire fraction is going to become positive. Whatever that is, put it in your calculator and find out. Okay, now this becomes x is great okay, make sure that you are not doing this stuff, that you multiply this by 10 and multiply this by 10 in order to convert it into log 7 upon log 5. This is log 6. This is going to be the most hideous of the mistakes. Don't do that. Okay, now so the answer is going to be x is greater than log 0.7 divided by log 0.6, or you can rewrite it as log 0.7 base 0.6, whatever. Okay, so this is going to give you the domain, the answer of this x. Now, why does this happen? I don't want you to memorize this, that whenever you are dividing it by a negative, the sign changes. But I told you the intuition that if you have a negative 0.28x here, and then it is less than, let's say, 0.35 here. Now, if I send this there and bring this here, so what does this become? This actually becomes 0.28x is greater than negative 0.35, and now if I divide it by 0.28 and divide here by 0.28, this becomes negative, this was also no, sorry, yeah sorry, this was also negative 0.35, right? This is what we did. So here this becomes positive, and now when I divide it by, so this becomes 5 upon 4 is greater than x, right? So this is the reason that the sign changes. See, although this sign still looks that, but now see that x is greater than. Here x was supposed to be less than, but since we are dividing both the sides by a negative, we directly change the sign, flip the sign over, right? So if you are given x times log of 0.6 is less than log of 0.7, and log of 0.6 is a negative, so what you're going to do is you're going to do log of 0.6 upon a negative, which is log of 0.6, and flip the sign over and write down log of 0.7 upon log of 0.6. This cancels and you're left with x is greater than whatever this fraction is going to be, or you can rewrite it as log of 0.7 base 0.6 by change of base law. Okay, so this is the intuition or the logic behind it. So now also let's recap this definition of logarithm, which is the inverse of f of x, that whenever this argument is between 0 and 1, the answer is going to be negative. Look here, I'm going to use the pointing device. So whenever this is between this range, the answer is going to be negative. Whenever it is 1, the answer is going to be negative, and whenever the domain is greater than 1, the answer is going to be positive. Please see that the graph does not exist for the negative domain, and we already learned it in our previous 2 lessons on logarithms, that the logarithm does not exist if this x is negative. It does not even exist if this x is 0. So 0 is not included. See? So x has to be strictly greater than 0 and less than 1 in order to produce negative values. It has to be equal to 1 in order to produce 0, and it has to be strictly greater than 1 in order to produce positive values, right? Positive values here. So we have recapped the definition of logarithms as well, which behave in this particular manner because it's an inverse of the exponential function, which you already know. Now, this is exactly the sort of thing examiners love. Most students know how to take logarithms. Most students know the power rule, but under exam pressure, they forget one simple question: am I dividing by a positive number or a negative number, right? That 1 second of thinking can save an entire mark. Never rush this step, right? Now, I'm giving you a question. I want you guys to pause this video and try to solve this yourself. So this is 3 to the power 2x minus 1 is greater than and equal to 8, right? Okay. So hopefully you guys have come to the same answer. Okay, I'm not solving it. I want you guys to comment the answer in the under the video. So you had to take logs, use the power rule, and then see if the inequality changes or not, and then simplify completely. Give it a go before I continue. Okay. Now we have seen how logarithms solve equations and how they solve inequalities, but the most beautiful application of logarithms isn't solving either of those. It is linearization, which I'm going to jump on right away. It's something Cambridge uses in modeling equations. So we use linearization in modeling. In the next section, which I'm going to jump on right away, we are going to use logarithms to make an exponential curve behave like a straight line. So if you have here a y and an x, and if there is an exponential curve. Now, what if I change this into ln and change this and keep this into x, what happens? What happens is now you have a straight line, and we are going to see why that happens. The process is called linearization. We turn the curve into a linear function, hence it gets this name linearization from this process. And once you understand it, an entire class of P3 questions suddenly become much easier. So far in this chapter, we have used logarithms to solve equations. We have used them to solve inequalities. Now we are going to see something completely different. In fact, this is one of my favorite applications of logarithms in the entire P3 math syllabus. Cambridge doesn't always use logarithms to find an unknown. Sometimes it uses logarithms to change the graph itself. Change the graph. This is also one of the uses of logarithms. Okay, let's see what I mean. So now, why linearization even exists? Why does it exist? Okay, now let's explore it. Suppose an experiment gives us the relationship. You are observing some of the values and you saw an exponential relationship between the observed variable and the dependent variable on that, right? So y equals to a times b to the power x. Now, where a and b are constants, so this is a constant, this is a constant, this is the independent variable, and this is the dependent variable, right? So you know all of this, right? Now, if we simply plot y against x, I can clearly see that when I take x as 0, I get here 1. When I take x as less than 0, my graph looks something like this. When I take x as 1, my graph is going to go to a times b, and then so on and so forth, right? Now, this is a curve, right? It's an exponential curve. And curves are difficult to analyze. You can't directly read the gradient, you can't directly read the intercept, you can't easily determine the constant. So mathematicians had a clever idea. Instead of changing the equation, why not we change what we plot, the axes? That is the whole philosophy behind linearization. We are not changing the data, we are changing the axes, what we are plotting, okay? Now, let's begin to do that. So if you have a function y equals to a times b to the power of x. Now you take natural log or a common log which is base 10. So let me take natural log. So natural log is log to the base of e. We call it ln. So if there is an x, so this is ln of x. So if you have ln, it means that it is of base e. Now this becomes ln. So ln has an argument of y. Whether you take natural log, which is this, or whether you take a common log, which is with base 10, or any other log, let's say log base 5, nothing matters. The behavior is going to be exactly the same. Now this is ln y equals to ln a bx. Now can you see that a is getting multiplied by b power x? So I can apply the product rule here. So this becomes ln a plus ln b power x. And now can you see right here that x is the power of an argument. So I can bring this down using the power rule. So this becomes ln a plus x times ln b, or can I rewrite it as x times or ln b times x plus ln a is equal to ln y. Now, we are stopping here. The single line is probably the most important equation in today's lecture. Now, beside this or under it, write something you have known since O level, which is y equal to mx plus c. And now we compare the two equations carefully. They are identical. So we simply match corresponding parts. So y m x c. So this y is equal to, wait, let me put the equal signs first. So this y is same as ln y. This m is same as ln b. This capital X is same as small x, and this small c is same as ln a. Right? This is what Cambridge is actually testing. Not whether you can memorize formulas, but whether you recognize a hidden straight line which was right here as soon as you applied the logarithm to the exponential curve. Now, why Cambridge changes the axes? Now, suppose I ask you to plot ln y against x. So now, if we change the vertical axis from y to ln y and we keep the horizontal axis at x, so whatever observed values of y we got against the observed values of x, let's take the log of that and now plot it. So now, notice what has happened. It's going to plot a straight line with our y-intercept or our vertical intercept at ln a and our gradient of ln b. Okay, we are no longer plotting y against x. Instead, we have changed the vertical axis from y to ln y, right? Now, that one decision transforms an exponential curve into a straight line, where this becomes now ln a, and this gradient is now going to become ln b. So this is ln b and this is 1. Rise over run, right? Sorry, this is ln b and this is 1 because of this, right? Now, and once we have a straight line, everything becomes easy. We can calculate the gradient, which is ln b. We can find the intercept, which is ln a. We can determine unknown constants. We can model real life data. And this is why linearization appears so frequently in a lot of disciplines, in physics, in chemistry, in biology, in economics, in engineering, and a lot of other disciplines as well, right? Because it simplifies the data that you observe. Now, Cambridge doesn't always use y equals to a times b to the power x, right? Sometimes you'll also see y equal to k multiplied by x to the power n. Previously, x was in the power, right? Now, x is in the base and a constant n is in the power of the variable and another constant is getting multiplied. Now do the same thing. Now you can either introduce natural log, which is ln on both the sides, or you can do common log. Because we have already done natural log, let's do common log, which is lg. Or so lg is same as log, is the same as log base 10. Okay, so let me write down lg. So lg here. So this is, I'm just using different variations so that you get accustomed to seeing those, okay? Now, apply the product rule again here. So this becomes, now I'm converting log lg into log, okay? And no base, which means the base is 10. So this is log k plus log x power n. And now I'm changing log into log base 10 because it's the same. I'm just making different things, right? So log k base 10 plus, now I can apply the power rule, bring this power down here. So n times log of x is equal to log base 10 and log base 10 of y. Now I will bring the lg again, and I'm doing it just because I want you guys to get accustomed with the fact that lg is same as log base 10, right? Now, easiest is lg, of course, and I can radically just remove this lg and introduce the natural logarithm as well, right? So ln. So ln y is same as, now let's put it in the same y equals to mx plus c form. So this is our variable. So ln y equals to the gradient, which is n, which is the coefficient of this variable, and ln x plus ln k. This log of base 10 is changed to ln. This log of base 10 is changed to ln. And this log base 10 also changed to, I've changed it across the entire equation, okay? I cannot do it just in one of the terms. I have to do it across the board. So now can you see that I can rewrite this as, I can compare it with y equals to mx plus c. So my capital Y, m, x and c now becomes, capital Y is ln y, m is n, x is ln x was transformed into capital X, and my constant is ln k, right? Notice something different. This time both axes changed, right? So y changed into ln y. So all the observed values of y that we saw, we are going to take the ln of those. And all the observed values of x are going to change into ln x. So if we had the observed values, let me do it here. So if you had observed values of x and y and you plotted an exponential curve, now take ln x of those values and ln y of those values. And now when you're going to plot these values here, this is going to give you a straight line where the gradient is going to be n upon 1, because this is n upon 1, and the y-intercept is going to be, or the vertical intercept or the ln y-intercept is going to be ln k. Okay? Now, as simple as that. Now, whenever you see a linearization question, don't rush into calculation. Do it calmly. The very first thing you should ask yourself is, what exactly has Cambridge plotted? Have they plotted y against x? Have they plotted ln y against x? Have they plotted ln y against ln x? Or perhaps log y against x squared? Who knows? Right? So you have to read that first. The axes tell you what the gradient and intercept actually represent. This one habit alone prevents many unnecessary mistakes. And now I know you guys will be quite perplexed. You want to put into practice and want to see how the Cambridge actually asks you a question. So now let's move into that. Okay, and I'm going to use a presentation marker. Now let's say variables x and y satisfy y squared equal to a times e power k of x, k times x, right? Where a and k are constants, right? Now the graph of ln y against x. So now they're saying that if you plot ln y against x, ln y against x, right? It gives you two value. It gives you two coordinates, 1.5 comma 1.2. So when x is 1.5, ln y is 1.2, and when x is 5.24, ln y is 2.7. Now you will notice that there is no ln y here, right? So now you are going to convert it into ln y, and how do you do that? You introduce natural log or the ln on both the sides. So I'm going to introduce ln here, and I'm going to introduce ln here, and I get y squared, which is as it is, and I get a times e to the power of kx. Now apply the power rule. This 2 comes in the front, so 2 ln y equals to, apply product rule, ln a plus ln e power kx. Now can you see that kx is in the power of e, so I can bring it down. So this becomes 2 times ln y equals to ln a plus k times x ln e. Now ln e is what I told you, that log to the base of e is ln. So ln e therefore is nothing but log e to the base of e, which is nothing but 1. We already did that log of anything to the base of the same anything is 1. So I can convert this into a 1. So now what do I have? I have 2 times ln y is k times x. I'm writing this first, plus, and then this second, ln a. Now also see, now because I am plotting ln y against x, I want to have just ln y on my left hand side. So I will divide both the sides by 2. So I get ln y equals to k upon 2x plus half ln a. Now notice something, this half ln a can also be written as ln a to the power of half, right? Which is one and the same thing. You can, if you can bring the power down, you can also take the power back to the, you can take the coefficient back as a power of the argument of logarithm. It is a coefficient of. Okay. Now, but we are not doing that. There is no need to. Now, they have given us 2 coordinates, right? They gave us 2 coordinates. One was 1.5 comma 1.2, which was x comma ln y, and the other was 5.24 comma 2.7. You can now Let me put the simpler one here. So this becomes lny. So lny is 1.2. So I'm not going to write ln 1.2. Instead, this 1.2 is the value of lny. So I will put 1.2 directly here in place of lny. Okay. Now k upon 2 is my gradient. X is going to be 1.5 plus half times ln a. Okay. Now this becomes what? This becomes okay, first of all, instead of doing all of this, oh my god, I got rid of the entire thing. Okay, I should have used a pen. Okay, let's do it again, don't worry. So this was y squared equals to, okay, so this is going to be a practice. So y squared equal to aekx, introducing ln on both the sides, give us 2 ln y equals to ln a plus kx, because as ln e is 1 and kx was brought down. So this is ln y equals to k upon 2x plus half ln a. Okay, and the two for x against, so ln y against x, we were given two values, 1.5 and 1.2. Oh, no, we were given 1.2 and 1.5. No, 1.5 and 1.2. Okay, yeah, that was right. And we were also given 5.24 and 2.7. Okay, now notice that this is the gradient of a straight line, right? Because we are plotting ln y against x, so this is nothing but a straight line. So now this becomes, so let's take the gradient of the system. So this becomes 2.7 minus 1.2 over 5.24 minus 1.5 equals to 1.5 over 3.74 equals to, now this is the gradient and the gradient is also k upon 2. So now let's do the cross multiplication. So this becomes 3 upon 3.74 equals to k. Okay, now this is approximately equal to 0.802, or let me just take k is approximately equal to 0.8. So we got the value of k. Now let me put this back in here. So this is ln y equals to k upon 2, which is 0.8 upon 2, which is 0.4, right? Or 0. This was 8 point, so I will take 0.401 times x plus half ln a. Now I also need to find the value of a. So how I can do that? I can just plug in this, either this coordinate or this coordinate into the system. So 1.5 and 1.2. So 1.5 is x, 0.401 times 1.5 plus half ln a equals to ln y, which was 1.2. So this becomes 1.2 minus 1.5 times 0.4 is going to be 0.6 approximately, times 2 equals to ln a. So this is 1.2 equals to ln a. Or, so this 1.2 is approximate because this is 0.401, so the value is going to be something different, but I'm just using the approximate values. Now ln a is nothing but log a to the base of e equals to 1.2. So now when I convert this back into the logarithmic form, this becomes a equal to 1 e to the power of 1.2, and again this is an approximate value. So this is as simple as that. So this is approximately going to be equal to 3.31, right? And this is the answer that you are going to leave. You are not going to leave your answer in this form, right? So this is a must. So a is 3.31, k is approximately equal to 0.8, correct to one decimal place. And with that, we have completed the entire logarithms and exponential functions chapter for Pure Mathematics 3. Across these 3 lectures we have covered this week: why logarithm exists, how do we convert from exponential into logarithmic form and backwards, right? Now, log base 10 is lg, or is simply log, and log base e is simply ln, and change of base law is log a to the base of b is same as log a to the base of c upon log b to the base of c, right? We have done that. We also did the power rules. We also did the quotient rule. We also did the product rules, right? And we applied those as well. We also solved logarithmic equations. We also solved the inequalities as well. We did the domain restrictions as well, which is extremely important. We did the definition that whenever the argument of x is between 0 and 1, it can't be 0, it can't be negative, but in the positive as well, if it is between 0 and 1, this is going to be this is going to produce a negative number. If it is 1, it is going to give you a 0, and if it is greater than 1, this is going to give you a positive. We did that. We also did exponential inequalities, right? In this very chapter, we also did exponential inequalities, and then towards the end, we did linearization modeling, right? Linearization and modeling, right? So this is what we do, and we try to do an exam question as well. So that's a huge chapter that we have, alhamdulillah, finished. If you have watched all 3 lectures carefully and worked through the examples yourself, you have built a solid foundation for one of the most important areas of A-level mathematics. Now here's what I'd like you to do. If this lecture helped you, subscribe to the channel. It genuinely helps us continue producing free Cambridge mathematics content for students around the world. If you know someone who's preparing for 9709 P3 or P1 or S1 or S2, send them this playlist. Studying with friends makes revision much easier, and it helps them avoid the same mistakes. Also, let me know in the comments which part of this chapter did you find the most difficult. Was it the laws, logarithmic laws? Was it the equations? Was it the linearization process, or what, right? I read all the comments, although there are very few currently because we just started our channel. But your comments really help me decide what to explain in even more detail. And for quick revision, examiner traps, and save-worthy summaries, follow Easy Taleem on Instagram. We go by the name of EASY Easy TALEEM on our Instagram, and you can also reach out to me on my WhatsApp for any queries. +923293028485. So you can reach on Instagram. We regularly post reels, carousel notes, challenge questions in the stories, and revision content designed specifically for CIE students. If you're looking for structured preparation rather than studying alone, we also have complete programs for AS and A-level mathematics, which includes live interactive classes, the recorded lectures, worksheets, regular tests, doubt solving sessions, 24/7 access on our WhatsApp, and complete preparation for October-November 26 retake or May-June 27 attempts. If you'd like to know which program suits you best, just WhatsApp me on +923293028485 or visit our Instagram channel and DM us. Finally, this chapter is complete, but this Sunday we begin one of the biggest and highest scoring chapters in pure 3 mathematics, which is trigonometry. And here we are going to cover identities, compound angles, the R formula, trigonometric equations, examiner shortcuts, and everything you need for Cambridge 9709. Until then, take care, keep practicing, and I'll see you in the next lecture. Allah Hafiz.